Good morning, sir. This is Jay Prakash from ECB section. My roll number is 24BQ1A0499. Today's seminar topic is random process. Definition, representations, examples, and types. Introduction about the random process. A random process is a collection of random variables that depends on time, t and the sample space of S. It describes how a random variable evolves over time. Example, the noise signal in a communication system. And the definition of a random process. A random process is also called as stochastic process is a function of two variables x of x comma t, where s is a sample point in the sample space, where t is the time variable. Thus, x of s comma t represents the value of process of a particular experiment s at a time t. Representation for each fixed t. X of s comma t is a random variable. For each fixed s comma, x of s comma t is a time function or sample function. Therefore, the random process can be represented as a set of time functions, one for each sample. Example 1. Tossing a fair coin repeatedly. Example, tossing a fair coin repeatedly, let x of t is equal to 1. If the result is head at time t, let x of t is equal to 0. If the result is a tail, the sequence of the heads and tails from a random process. Example 2. Random noise signal in a communication. The amplitude of a noise at any instant it is uncertain. Represented as a x of t, where each realization sample functions shows one possible waveforms. I repeat example 2. Random noise signal in communications. The amplitude of noise at any instant it is uncertain. The amplitude of noise is an instant t is uncertain. Represented as x of t, where each realization samples function shows one possible waveforms. Types of random process: discrete time, discrete state, continuous time, and continuous time. First of all, discuss about the discrete time. Discrete states process both time and time t and the amplitude take discrete values. Examples: binary signals. Binary signals 1 or 0. We can take 1 or 0 sample at a fixed times. Continuous signal. Discrete states process time is continuous. Time is continuous, but amplitude takes a discrete value. Examples: Poisson process. Type of random processes: continuous time. Continuous states process both time and amplitude are continuous. Example: thermal noise or Brownian motions. Mean of a random process. The mean function is given by mx of t is equal to accepted value of x of t, where accepted value of x of t is the accepted value of x of t at time t. Autocorrelation function. The autocorrelation function is defined as the Rx of t1 comma t2 that equal to accepted value of x of t1 convolution x of t2. It measures the similarity of the signals at two different times and t1 and t2. Variance of a random processes and it differentiates. Variance is a measure of the depression of spread of the random process values around the mean. It represents the average power of a deviation of the process from its mean, and its formula is sigma x square of t is equal to accepted value of x of t minus mx of t whole square, and the alternate form by using autocorrelations, sigma x square of t rx of 0 minus mx of t whole square. If the process is stationary, sigma x square is equal to rx of 0 minus mx whole square. Let us solve a problem on mean and variance of a random process. Given x of t is equal to x of t is equal to a cos omega t plus theta, where theta is the uniform distribution over the interval of 0, 2 pi. First, mean of the processes. You can calculate the mean of the process. Accepted value of x of t is equal to accepted value of e of a cos omega t plus theta, that equal to 0. Therefore, mean e of x of t is equal to 0. Variance of the process, variance of x of t is equal to rx of 0 minus e of x of t whole square, rx, that equal to rx of 0 is equal to a square by 2 cos 0, that equal to a square by 2 by 1, that equal to a square by 2. Therefore, variance of x of t is equal to a square by 2. And the problem 2 about the by solving the by autocorrelation function. Given x of t is equal to a cos omega t plus theta, autocorrelation function rx of tau, that equal to e of x of t into x of t plus tau. By using the trigonometric identities, rx of tau equal to a square by 2 cos omega t. I repeat my question. Given x of t equal to a cos omega theta, by autocorrelation function rx of tau is equal to accepted value of x of t convolution of x of t plus tau. By using the trigonometric identities, rx of tau, that equal to a square by 2 omega t, and the final answer is x rx of tau equal to a square by 2 cos omega t. And the stationary random process, and the second part is the stationary random process. A random process is said to be stationary if its statistical properties, mean, variance, autocorrelations, and moments do not change in with time. Example: thermal noise, electronic circuits. There are two types: first order stationary process and second order stationary process. They are equal to and dependent, does not change with time. And the summary, a random process is equal to a collection of a random process variables over time. A random process equal to a collection of random variables over time. Representation x of s comma t. Important parameters: mean, autocorrelations, variance, moments. Example: tossing a coin, noise, Poisson problem. Classification based on the time and interval and discrete or continuous. Stationary random processes are divided into two: first order stationary random process and second order stationary process. First order is a process is said to be stationary for if its first order or the first of the statistical mean does not change with time. That is called e of x of t is equal to x of t into x of t plus tau. Importance parameters mean, autocorrelations, variance, where random process is equal to a collection of random variables over time. Important parameters mean, variance, autocorrelations, moments, example tossing a coin, noise, Poisson process, and the classification are based on the time, state, discrete, or continuous. Thank you.